This video abstract is AI generated. How do we know which parts of an RNA molecule are truly exposed to solution? RNA structures are often drawn as static helices, loops, and bulges. But RNA is dynamic. Bases can stack, unstack, flip out, or become temporarily exposed. This manuscript asks whether a small soluble paramagnetic molecule, TEMPOL, can be used to measure RNA surface accessibility directly by NMR. The idea is simple. TEMPOL diffuses freely in solution. When it approaches an RNA proton, its unpaired electron causes paramagnetic relaxation enhancement, which weakens the corresponding NMR signal. Stronger attenuation means that atom is more accessible to bulk solvent. By comparing proton-carbon HSQC spectra recorded with and without TEMPOL, the authors convert signal loss into an accessibility index. The first test was the stable HIV-1 frameshift stem loop. Because this RNA is well structured, TEMPOL accessibility should mostly follow the known structure. That is what happens. The tetraloop and helix ends are more accessible, while the O-form helical core is more protected. The method is even sensitive enough to detect subtle differences between purine and pyrimidine aromatic positions. But the most interesting result comes from the loop. Some tetraloop nucleotides show unusually high attenuation, even though they appear stacked and relatively buried in the NMR structure. This means TEMPOL is not just reading the static model, it is detecting transient loop motions, likely base and stacking events that expose nucleotides to solvent. The authors then moved to a dynamic RNA, the U6 intramolecular stem loop. This RNA contains an internal loop that undergoes a pH-dependent conformational switch. At high pH, a 79 is mostly unprotonated and unusually accessible. At low pH, a 79 becomes protonated, a C67-79 wobble pair is stabilized, and the neighboring U80 base flips out. TEMPOL captures this transition directly. At low pH, attenuation of a 79 decreases, consistent with a 79 becoming protected in the wobble pair. At the same time, U80 becomes more accessible, consistent with base flipping. Molecular dynamics supports this interpretation by revealing internal loop conformations that are more exposed than expected from the original NMR ensemble. The final message is that TEMPOL probing provides a practical NMR readout of RNA surface accessibility. For rigid helices, accessibility follows structure. For flexible loops and switching regions, accessibility reveals dynamics that may be hidden in static or time-averaged models. To know more, read our work online.